Good morning, students. I tell you, when we get this rain in the air and I run in the morning, then the allergies kind of kick in. Again, the beauty of living in Houston area is it's nice and warm, but all the hurricanes blow in all kinds of allergens and things, and that messes with my big old head here. But I'll be fine. I hope all of you all are doing well and staying healthy. It's important, like I said before, to keep working on trying to stay safe and wearing the mask. On Sunday, we had our first service back at First Presbyterian, and I had to wear a mask when I played, and that was odd, but that's what we have to do, and it will hopefully help to keep us safe. Now, I want to remind you that you'll have your second test this week with the same, I put the announcement up with the same window of time. We won't have class on Thursday to give you an opportunity to rest or sleep in, as you say, or study or catch up on homework. And what I want to do today is just kind of give a short recap of what we did last class with the unit circle, and then talk about the trig graphs for the cosine and the sine. So our study at this point has focused on the unit circle and computing via the unit circle. You know, dividing out multiples of 2 pi, setting those to 0, and computing reference numbers. And I gave you a lot of techniques with that, and also the Pythagorean identities and the even and oddness that we get with the 6 trig functions. So lots of basic ideas, but very important. So first, what I wanted to do before we start talking about the graphs is to just look at an example where we do a computation based on what we learned last week. Now, there was a problem, lots of times. Let me move Professor Ron over just a little so I can see my screen. What we found last time is that we can actually do computations with negative angles because we have a counterclockwise direction that corresponds to the negative real numbers, excuse me, the clockwise direction that corresponds to the negative real numbers, and then the counterclockwise that corresponds to the positive real numbers. So we basically map out the real line with the unit circle. And so I did some computations where we started with the negative angle, we divided out the multiples of 2 pi, and then made it positive to apply the reference number rules. So what I want to do here is maybe not have to work as hard for just as a review or practice. I just want us to compute the sine of negative 27 pi over 6. Now remember, when there's not a pi in it, I gave you some of the 2 decimal approximations with pi that will outline the unit circle to give you a way to basically figure out where the t lies. And that's a very useful approximation, so don't forget that. Now first, if we want to compute this, let me just go ahead and write the problem down here. We know that the sine function is odd. Now we talked about how you could prove that last week. We did a picture proof, and then we did a more rigorous proof, and it really just hinges on the definition of reference number and the sign convention from the unit circle. Now again, remember, we start with the unit circle and we define all of the x coordinates on the unit circle to be the cosine of t, and we define all the y coordinates to be the sine of t, and then we take reciprocals of those and ratios to get the 6 trig functions. But now first, we know that the sine function is odd, so we'll go ahead and factor this. This is what you're doing in section 5.2. You probably already started on this. And remember, our second test will not cover any trig. I want you to get good with your trig, but you won't have any trig on this test, just to give you a little breathing room. But don't get used to that. We have to focus and get our work done. Now first, here we've got the negative factor, and then of course we can divide 27 by 6 just using the division algorithm to see if we have any multiples of 2 pi, which we clearly have. So 6 into 27 will go 4 times, so that'll be a 4 pi. And we have a remainder of 3. So 27 minus 24 gives us 3. So we have 3 pi over 6. So before I did all these calculations outside of the trig function, and I want to show you, you can actually do them within the trig function now that we're a little bit more comfortable. But you use whatever method works for you. I just want to show you ways that you can streamline your work, but the concepts can be executed in many ways. Now, of course, I don't have to use a congruent symbol because we're doing the sine function. But remember, 2 pi is just equivalent to 0. That's just 2 times around the unit circle, actually going in the counterclockwise direction because this is positive. And so we just set that to 0. Again, modulo 2 pi. And of course, 3 pi over 6 is just pi over 2. Now, of course, pi over 2 is on the axis. It's on the y-axis here, right here at the pi over 2 radians. So y-axis, not in the quadrant, the boundary of the quadrants 1 and 2. And we know that value is 1, so we just get -1. So the idea here is that if we have some convenient multiple of pi that's on the unit circle, we can actually get an exact value. Maybe the best we can do is just get rid of the multiples of 2 pi and then just write the expression exactly. Maybe we get an input here that we don't really know anything about, at least for now. And so we would just stop there, just like we might say base e raised to the 1/2 power. We can use our Google calculator to approximate that, but if we want the nice exact calculation, we just leave it alone. The same is going to apply for the trig functions. But right now, I want you to get really used to using the unit circle, just like we have here. When we have our pi over 2, we have the y coordinate is the sine function, and that's where we get the 1. And then, of course, the negative is built in to the odd condition of the sine function, so we get this. So again, very simple. You do the same thing over and over and over. Hopefully, this is becoming more convenient for you. And as I talk to other students, they're starting to get the idea of what's going on here. So just remember that practice with the unit circle is going to make you a lot more confident. Keeping track of signs, that's what's important. Now, before we actually write down the trig graphs and talk about new parent functions of cosine and sine, I want to do one more algebraic. So this was practice number 1. I want to do one more algebraic expression. So I want us to write secant t in terms, this is like your WebAssign problem, in terms of cotangent. And we're going to say that t terminates in the 3rd quadrant. So as you measure along the unit circle, you stop in the 3rd quadrant, and that's where the terminal point is, okay? So we would say terminates or element of 3rd quadrant, meaning that as we move along the unit circle, we stop in that 3rd quadrant, and we are corresponding with a corresponding terminal point. Now, of course, when we think about that, we just kind of do a little sidebar here. So in the 3rd quadrant, x is negative. So that means that secant t will be less than 0. And then, of course, cotangent, that's just cosine over sine. And remember, in the 3rd quadrant, x and y are both negative. So cotangent t is positive. So anything that we would work with in this particular algebraic expression would have to satisfy these conditions. So this is what we have to, so again, if you don't know where the t terminates, then you would only have up to plus or minus here. And we want to be specific. So now, what if we go to our Pythagorean, because that's about all we have. So secant squared t, remember that's just 1 plus tangent squared. That's the Pythagorean identity. Now, of course, we want to use cotangent, so we know tangent is the reciprocal of cotangent, so we can just write this as 1 plus 1 over the cotangent squared. using our reciprocal identities. And of course, I'm using the shorthand notation for tangent of t quantity squared. Remember, this shorthand notation may be a little odd right now, but it's going to be what's going to help us make our work a lot more efficient. So please get accustomed to using these. Now, of course, just to remind you, like when you're typing in WebAssign, the parentheses come up. So for instance, this would be equivalent to the following. WebAssign likes to use a lot of parentheses, and so it could be written as tangent of t quantity squared. So we don't have to write all these parentheses. We use this notation, and it's very convenient, but know that this is equivalent to this. The argument is t, and we're squaring the tangent of t, and that's the notation we use for it. And this is universal, ladies and gentlemen. I didn't just make this up. Everybody uses this. So as you communicate with your STEM professional colleagues, they will use this too. So now what we want to do is just get a common denominator. So secant squared, just to make it look nice, we get, well, we'll have a 1 plus, and multiply this 1 by cotangent squared. Again, that's another Pythagorean identity, but we want to leave everything in terms of cotangent. So we don't go forward to go backwards. And so now we have the square of the secant, but we know that the secant must be negative in the third quadrant. So this select negative radical. So all of this is based on the sign convention of the unit circle. There will never be any issue about sign, ladies and gentlemen, because you know X and Y values are signs in each of the quadrants. So there's never any guesswork. If you guess at this, then you're just ignoring this. You're ignoring the unit circle. Don't do that. Don't guess at anything. I mean, everything's clearly written out here, and that's how you're going to move to the next level. So now we're going to say secant t will just be the negative radical of the whole thing, and then we'll break it up. So now we can use the laws of exponents and apply the radical to the numerator and the denominator. So we'll just leave our negative upstairs. Some of these are long-winded, some are less, and then of course the square root of the this. Let me just write this down. The square root of cotangent squared t is just the absolute value, just by definition. And now, of course, the cotangent t is positive here, so the absolute value is actually the positive. So that selects the correct sign for the cotangent. So now this has the appropriate sign. In the third quadrant, the cotangent's positive, the principal square root's positive, and then the negative makes the entire expression negative, which corresponds to secant being less than 0. So when you do these expressions, you don't guess about the sign. You make sure that the sign is represented by the expression. Maybe the sign is carried by one of the trig terms. Maybe the sign is carried once you apply a negative. The idea here is that we use the negative as a means to represent the sign here of the secant function, because we terminate in the third quadrant. This will take some practice, but again, you don't have to get this overnight. As you do some of these, some will be very easy, just a few steps. This has more steps, but the steps are all valuable. Just remember, when we do the square root of the square, that by definition is absolute value. When we flip this around, of course, this is different. When we square the radical, we just get the radicand. That's completely different. We don't have absolute value there because it's assumed to be well defined. But when we go in this direction, we're forced to carry the absolute value. And then of course, if we want to remove this, we'll have to make some restriction on the input t in order to move the problem forward. The restriction here is given in the problem, so we didn't have to set that forward. Okay, so the idea is that now we can work with the unit circle. So what we want to be able to do, ladies and gentlemen, is to talk about how the unit circle generates function graphs. Now, graphs are useful because as you do your STEM work in physics and engineering and all, it's nice to have a graph. So first, we'll just say y, we'll just do the parent, y equals cosine of t. Now, normally when we're dealing with the unit circle, we will use the variable t. So I'll just say, for instance, this is how we've used t as measurement, along unit circle, along S1. This is the convention that we've been using. So for graphs, you can still use the same letters, but for graphs, just for convenience, we replace t with x. So it doesn't change the definition. You could still think of x as measurement along the unit circle, but we're going to look for a more convenient notation where we have input x, the x-axis, and the y-axis. But clearly, we can have problems where t is input as the horizontal axis. But the WebAssign uses x quite often, so I want you to get used to that. But again, it doesn't matter. Now, so this will imply we're looking for a parent function y equal cosine x. Now, when it comes to graphing a cosine function, what I like to do, what Professor Ron likes to do, is look at the principal points from the unit circle. And these are the ones that follow. That is values of x and cosine x. These are straight from the unit circle. And if we can move these so-called points, then we can fill in the details because I'm going to develop a shape for the cosine function. Again, we don't have calculus, so we have to use our imagination, but I think we'll be okay. We're able to get the square root function by plotting 500 points, or at least your calculator would do that. And your teachers would always say, okay, this is what square root looks like when we plot a bunch of points. So we're going to do 0. We're going to do pi over 2. We're just going to move along the axial points. Pi over 2, pi, 3 pi over 2, and 2 pi. So we're going to loop once. We're going to go around once. And then, of course, as we do horizontal stretching and compression, these numbers will change, but the corresponding outputs will be dragged along with them. So again, this will be like function transformation. Of course, cosine of 0 is 1. Cosine of pi over 2 is 0, just using the unit circle. Cosine of pi is -1. Cosine of 3 pi over 2 is 0. And then, of course, cosine of 2 pi is 1. So that's just looping around the unit circle. So now I want to make a comment here. Based upon S1, the values of cosine x repeat as we cycle through intervals of length 2 pi. That is, the 2 pi is like a 0. If we input an x and we add a 2 pi to it, we just loop around the unit circle and it's as if we didn't go anywhere. And then you're thinking, well, any multiple of 2 pi will put us right back at the x. So what we can do is think of a positive number. For instance, this will imply that cosine of x plus 2 pi is actually just cosine x. Now, this 2 pi has a very special significance. It's a positive number, and ladies and gentlemen, it's the smallest positive number for which this is true. We call 2 pi the period. It's called a period. Usually it's called the standard period because it's the smallest possible real number that has this impact. So in general, right now, we will just say 2 pi is a period of cosine. Actually, 2 pi is the smallest positive real number, is the smallest possible positive real number, such that cosine x plus 2 pi equals cosine x. So it basically has a more distinguished standing. So we say cosine is 2 pi periodic, in the sense that we are focusing on this minimal value. So we call usually we use a letter T for period, but we've already been using T for distance along the unit circle, so we won't do that. But the thing is that even though we're distinguishing this 2 pi, any period of cosine, I mean, they're infinitely many. If you take any multiple of 2 pi and add it to x, as we already know, it does not change the output of the cosine. So if 2 pi is a period, then any integer multiple of 2 pi is also a period. So we say if, say, n is an integer, z, then cosine of x plus 2 pi times n will also be cosine x. So you can add any that's why I keep saying when we look for multiples of 2 pi here, we just set them to 0. Because again, that's not going to change the output of the cosine. So adding any multiple of integer multiple of 2 pi to what we call the x, the input, or sometimes we call it the argument, does not change the value. So if I look at these as principal points, these basically put a boundary on an interval of length 2 pi here, intervals length 2 pi. And so this gives us all the character of the cosine function. And then after this, we just repeat the same values going in the positive direction and the negative direction. So again, any multiple of 2 pi is a period for cosine because it always does this. But the more famous one, the reason we say 2 pi periodic here is because 2 pi is the smallest such positive number for which this is true. And so it's really an abuse of terms just to say 2 pi periodic, but we're focusing on the 2 pi as being the smallest positive. So that's how the terminology works. And so if you like, we can go ahead and plot these points and get a nice curve. That is, in order to draw a cosine function, all we need to do is to give the shape for a period. that is an interval of length 2 pi. And since it's kind of convenient here, this will be our parent function. It's not shifted, it's not stretched, compressed horizontally or vertically. And so we're just going to go ahead and think, now, what's going on here? Well, notice here, we've taken this interval right here and we've divided the interval length by 4. So here's how I came up with this. 2 pi, the interval length is 2 pi divided by 4 is just pi over 2. So these units of pi over 2 develop these 4 subintervals. 1, 2, 3, 4. And so when we graph a cosine function, we start with 0, and then we mark off pi over 2, which is the first interval. It could change depending on the transformations. Then we have pi. Then we have 3 pi over 2. And you space these, with equidistant. You don't have to be a computer generated plot. We know that these are all the same distance apart. So you do yourself a favor. Now, in some cases, we keep the same denominator to keep from going crazy if we've got really strange numbers. But these occur so often on the unit circle that we're okay with this. And now we can mark off a 1 and a -1. So just like with the parabola, we can go ahead at 0, we have a 1. At pi over 2, we have 0. At pi, we have -1. Now you can see why starting with the unit circle was so important. It gave us all of this for free. 3 pi over 2, we have an output of 0. And then back to 2 pi, an output of 1. Now, this does not plot the graph, but we have a nice smooth continuous curve that connects these points. That's the cosine curve. Now, if we plotted 1,000 points, we get a nice differentiable continuous curve, just like the logarithm and the exponent. So I'm going to fill in the curve. So again, depending on how stretched the curve can be, this is the basic shape of the cosine. Again, when you get to calculus, you're going to know why it has the downward concavity here and upward here and then downward there. That's kind of like polynomials. We have to cheat a little bit. So instead of plotting 1,000 points, we can actually write our parent function, and it will always have this similar shape. So the cosine function kind of looks like a polynomial, but the standard cosine function is bounded. Remember, it's bounded between -1 and 1. So this doesn't, it looks polynomial-like, but it doesn't have end behavior to infinity or -infinity or some case like that. So remember, with the cosine function and even the sine, we can stretch it and we can compress it vertically. And we can also stretch and compress vertically, or excuse me, horizontally, just like we did in functions with the previous sections with the college algebra review. So the idea here is that this is the new parent, so to speak. This is y equal cosine x. And so you can write this as the x-axis and the y-axis. Now, again, if you wanted to continue on, you can continue the curve here. You can just simply replicate this, put another copy here, put another copy here. So when you actually write the graph, all you need is a period. You need a period. You need the graph that is mapped over an interval of length 2 pi, or whatever the period of the function might be. It may be changed. So once you get one interval of length 2 pi, or whatever the period is, you have characterized the entire graph, because then you just replicate this, repeat this over and over. That's why we call this a periodic function. Even the visual part is periodic, and the algebraic part is periodic. So most students will say, well, which interval should we use, Professor Ron? Well, what we're going to do is we're going to move these points, and these points will give us the endpoints of the new interval, so to speak. And that will answer that question for you. So these points will be shifted maybe, or compressed or stretched, and the new points give us the new interval, and we're good to go. So just like we did with the previous types of examples, we'll do the same for this. Now, I want to go ahead and do the same thing for the sine curve. And you're thinking the sine curve is just a shift of the cosine curve. If you're thinking that, you're exactly right. So for sine, let's just go ahead and write down the principal points. So y, and we won't, and again, it's no shocker. The sine is also 2 pi periodic, so we don't have to repeat all that discussion. So y equals sine x. And we'll just say where n is an integer, we know that sine of x plus 2 pi n, that is add multiples of 2 pi, positive or negative, this would just be sine x. And by the same discussion, any multiple of 2 pi is a period for sine because we just get x. Adding this does not change the output, but we will say sine is also 2 pi periodic because this is the smallest real number for which this is true. So we use the same terminology. We like to distinguish the smallest positive just for convention. But like I say, any multiple of 2 pi is basically a 0. So we think in the unit circle, if we're not doing anything except working with the plain sine and cosine functions, we think of our arithmetic modulo 2 pi, okay? So now let's do our principal points like we did before and get a nice picture. And if you look at the graph here, you're thinking this is just a left shift or a right shift of the cosine function. You're exactly right, because you're thinking, boy, this because of all the symmetry on the unit circle, it's no surprise that this happens. So sine x, so again, we'll do the same points that we find along the axes because they're easy. 0, pi over 2. So these would be what I call the principal points that'll help us graph the function. We plot the principal points, or maybe sometimes we just cheat and don't do much at all because it's so simple. I mean, that can happen too. You don't want to knock yourself out, but you don't want to guess either. So now, of course, sine of 0 is 0. Use the unit circle. Sine of pi over 2 is 1. Sine of pi is 0. Sine of 3 pi over 2 is -1. And then, of course, sine of 2 pi is 0. So again, this runs through the principal points, an interval of length 2 pi. So let's get our parent function for sine. Again, all we need is one complete period. That is, we need to graph this function over an interval of length 2 pi. That will completely characterize the graph of the sine function. And again, we do the same thing, 0. These are going to be equidistant. So we're always going to take the period and divide by 4, or if we do the transformations, we get it for free anyway. So there's all kinds of nice things about transformations as we move points. The dirty work is done for us as long as we do our arithmetic correctly. And so now let's just generate another parent function. Remember, the sine function is bounded. This is really new, ladies and gentlemen. We haven't dealt with a lot of bounded functions. Our functions are rarely, well, you know, and not a surprise, right? Now, of course, if we think of arcs of a circle, that's kind of what we're working with. Those are bounded, but that's the same thing we're doing here. But in our work in college algebra, most of our ranges have been unbounded. So we've got some new objects here. So of course, at 0, we get 0. At 1, excuse me, at pi over 2, we get 1. At pi, we get 0. And then at 3 pi over 2, -1. And then, of course, at 2 pi, we get 0. So now we can sketch in our sine curve. So again, when we think of what we've done before, this again is the parent function. And when we want to manipulate parent functions, we can use the transformations that we again encountered in our college algebra review. So there's absolutely nothing any different here. Again, when you think about this, if you think of the cosine curve, let's just draw it in blue. So this is y equal cosine x, and I'll put a little red box around this. There. So if you look here and you think about what's going on here, you can see that as we look at the sine curve, it's just a right shift. If you shift the blue curve to the right by pi over 2 units, it will coincide with the sine curve. So this implies, well, at least from a picture, that sine x is just a right shift of the cosine curve. So we say cosine x minus pi over 2. Just as a visual. So from the unit circle, the way we've defined everything, we're thinking, well, my goodness, these curves are just shifts of each other. Why do we care about them? Well, the thing is, ladies and gentlemen, is that even though these curves are very connected, they are very different in the sense that there's zeros. Again, everything's shifted here. It's not so simple. The beauty of the sine and cosine function is that even though they are very similar, they lend such a richness of calculus that they are still considered independent functions. You're thinking, what about tangent? Tangent's just the ratio. Why do we care about it? Well, the richness of these transcendental functions is literally amazing, ladies and gentlemen. And so, like I say, with other curves, we don't get this bounty of output that we do here. And you're thinking, wow, for functions that are so closely related, we're going to see a whole lot of beautiful mathematics. So now you're going to think, oh, this is a nice shift equation. Later on, we will come back to this and we'll have another way of showing that this is valid. Here, we just kind of looked at the picture. So it's kind of like, all right, well, we agree with that, Professor Ron, but that's not the level of rigor you usually use. So what we'll say is that we will think about modifying this a little bit. But when we consider the way we've set up the unit circle, this would always be the case. So again, if we go back to the unit circle and consider how it's constructed and how we define sine and cosine, then this is definitely true, basically by definition. So whoever decided to go to the unit circle to think about the trig functions was a very smart person. And we are grateful for that. Okay, so now what we want to do, ladies and gentlemen, is look at a more generalized equation. So if we want to be able to graph sines and cosines that are transformed, we need to learn some new terminology. So we want to look at the transformed equation. So put these on a note card and commit them to memory. And just like we've done before, where Professor Ron would take a few points and move them, we'll move the principal points, we'll plot them, and then we'll connect the curve just like we did here using the shape that we have here from the parent function. So the transformed equation will be this. What we're going to do is we're going to set k to be a positive number. Then what we're going to do is write, and I'll just use the sine function. This is the notation that Dr. Stewart uses. We'll say y equals a times the sine, and we can use parentheses or brackets, it doesn't matter. We'll have k, and then we'll have x minus b. Again, we're always going to assume that the k is positive because the idea is that if it were negative, we could always factor. Since sine is odd, we could always factor a negative, and if cosine being even, the negative would absorb. But just for reasons of this setup here, we will make the assumption that k is positive. You could always make it so. So this is consistent. So now what we're going to say in this particular case is that since this is a bounded function, we're going to say that the amplitude, just as some additional terminology, the amplitude will be the absolute value of a. For instance, when we think of the amplitude of the sine function here, we see that's 1. Basically, the amplitude considers basically cutting the function in half vertically and then considering that distance right here. So that's how we define the amplitude. It's basically the coefficient of the sine or cosine function in absolute value. So here we would think of the amplitude of cosine and sine as being 1. And then we define the period. So now this will be the the horizontal compression and stretching. We know that the standard distinguished period is 2 pi. And then of course, that will be divided by k using our horizontal compression stretching. And of course, if k is between 0 and 1, this gets bigger. If k is greater than 1, this gets smaller. So that's consistent with the theory that we had from our function transformations. And then the very last one, again, we call this the horizontal shift or the phase shift. So we'll say the horizontal shift. Notice we have a negative here. Horizontal shift or phase shift. Which we'll just call B. So what you're seeing here is that if we arrive at an equation, just like we've done before, we want to make sure that the argument is factored so we can read the k. We have the x isolated and the minus b so isolated, so we can actually read these. So when we think about this, this will be the horizontal compression or stretch. This will be a vertical stretch or compression depending on the size of A. And then of course, the other thing is if we have a negative, that would be an x-axis reflection. And then of course, this will be horizontal shifting, just like we had before. Now, the thing is, when you take physics, you may make some modifications of these, but these basically come from the study of harmonic motion, and physicists love to be able to talk about these quantities. And so I'm just sharing this with you, but there's often variation here with how these are written. When this is factored, we think of this like we did with our function transformations. So just be aware that as you read other textbooks and science books, there might be some slight variation here, but these usually are pretty much steadfast. Now, The same goes for the sine function or the cosine function too. You can write it the same way, but this will be kind of like our standard transformed equation. So let's see how that works. So this is actually kind of interesting. Let's start with a simple one, and then we'll amp it up some. So say we have y equals negative sine 4x. And here what we want to do is sketch one cycle. That is a complete period, so to speak. And when we say complete period, we say interval of periodic length. So if we can sketch a function over an interval, that's the length of the period, we will have completely characterized the sine or cosine function. And so you don't have to draw 5 or 6 periods. So WebAssign will say, which is the correct graph? Well, you'll sketch it just like I'm going to show you here, and then you can choose. So now, of course, we can look at this and see that this is somewhat simplified. Now, notice here, if you like, we can go ahead and say now that the amplitude, it's already factored, isn't it? Amplitude will just be the absolute value of -1, which is 1, because we see that the A here is -1. That is, A equals -1. And then the K is 4. K equals 4, which implies that the period equals the standard, the distinguished period, 2 pi, divided by 4. And that will just be pi over 2. So the idea here is that if we can get the principal points, then we can actually label them on the graph and have some security that, okay, this is a legitimate graph. We didn't just kind of sketch a little curve that goes up and down and then said, well, that's reasonable. No, that's not reasonable. Remember, in all the transformations, we always have transform points. So now we can look at this and say, this is just a function transformation from the parent function sine. So let's write it down. So we have our parent, which is sine, just like we've done before. Well, with no 4, of course, that's the transform part. So we start with the parent, just like we did before. If you paid attention to what I did before, then this will be trivial. I mean, this is a break. Okay, so first, if you want, we can go ahead and do the horizontal compression. So H compression by 4. So we get sine 4x. So obviously we've made the period smaller by a factor of 4. So it's 1/4 as large. And then the negative would just be an x-axis reflection. This is the Professor Ron part, because there's nothing different here between what we've already done. And I don't want you to think of it as any different. You don't have to learn any new techniques. The only new part is really the period. We're doing a periodic function now, so that actually makes our work a little bit easier, but maybe a little bit harder because it's new. And then you think, okay, well, this will be what I need to do to the principal point. So let's write them down. We have 0, 0, pi over 2, 1, pi, 0, 3 pi over 2, -1, and 2 pi comma 0. Now, of course, if the fractions get messy, we can live with it, but we might want to use common denominators to keep from going, crazy. So now, look, we do H compression by 4. So that means all of the X coordinates get divided by 4. So let's do that. So we get 0 over 0. And then we divide by 4 here. That's going to give us pi over 8. We divide by 4 here. That gives us pi over 4. We divide by 4 here. This gives us 3 pi over 8. And then we divide by 4 here. That just gives us, 2 pi over 4, which is pi over 2. We did that, obviously. Now, this is where you could say, if we wrote everything with the denominator of 8, then you would see that they were spaced equidistantly. So I'm just going to add an extra little thing here. This is just completely extra. But I want you to see what's going on. This is the whole idea, reason I do this. You won't have to do this all the time, but I just want to see. Let's get a denominator of 8. So we get 2 pi over 8, 0. 3 pi over 8 we already have. And then, of course, this will be 8, so that'll be 4 pi over 8. So what I'm just showing you here, these are all equidistant. They're all spaced by a real number, pi over 8. 1 pi over 8, 2 pi over 8, 3 pi over 8, 4 pi over 8, which is that number right there. So this is the beginning of the interval. This is the end of the interval. And of course, you could have left them like this. That's okay too. I just want you to see what's going on here. So we take these points and we transform them to this. And then lastly, we do the x-axis reflection, which is we multiply all of the y coordinates by -1. So we get 0, 0, pi over 8, -1, 2 pi over 8, 0, 3 pi over 8, -1, and then 4 pi over 8, 0. Now, of course, when you think about this, when you've got a more complicated graph, this is indispensable. When you think about this, you're thinking, oh, okay, well, I'm compressing the graph and I'm doing an x-axis reflection. So you could probably kind of guesstimate things. But I don't really want you to do that, because if you're actually going to do this correctly, you need to identify one complete period, so to speak. You want to identify an interval of periodic length. And so now when you draw this, here are the new points right here, just like we've done before. And the length of the curve or the interval, of course, is pi over 2. So we have our 0, and we go ahead and just mark these off. Pi over 8, 2 pi over 8. I'll just put everything with the common denominator. You don't have to do this, but there'll be times when you want to, because you just want to have a nice, beautiful graph where everything is coordinated. And then 4 pi over 8, which is pi over 2. And of course, we have 1 and -1. So you can spread out the scale however you like, ladies and gentlemen. Of course, computer generated, the scale on the x-axis may be different from that on the y. You're still going to get the right shape. It just may look different with the generated plot from WebAssign. So now 0, 0, pi over 8, -1, 2 pi over 8, 0. I mean, this is easy, isn't it? 3 pi over 8. Here, let's see here. I've got, when I did the negative, 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 That should be the positive here. Sorry, get rid of that. We made that negative. The math always tells you and you make a mistake. So that's the positive. And then back to 0. So remember, when we go here, when we multiply the y's by the negative, that becomes the positive. So now we can sketch the graph. Now what I've done here is I've stretched everything out, but here the thing is that this is a quarter of the original graph. The original graph would stretch out just way out. For instance, when you think of this, the other graph would just continue on down here, stretched out. So what I've tried to do here, you don't always have to have a source of comparison, but when you look at this, you're seeing that the new cycle length, the new interval for the complete period is 1/4 of the original. So this only stretches from 0 to pi over 2. So you're basically getting 4 cycles of this graph, whereas in the original graph of the parent, you only get 1 cycle. So this completely identifies. And then of course, you've got your points here. So if you're working a problem where you need to identify some points, you have your points right here, clearly written out, mapped out. And again, this is a very nice procedure because you know the shapes, and you can, this procedure actually allows you to check your work as you move through, getting common denominators if you want. Again, equidistant. The principal points are equally spaced. That way you get a nice clean graph, and you can use the shape of the parent function to fill in the curve. Again, it doesn't have to be a work of art, but this is a complete representation of this curve. And then we just replicate this particular curve over and over to generate as many cycles of the curve as you like. Again, very simple, just like what we've done before. The new idea that's going to take a little bit of practice is just the factoring part and the period. That's the new part. Otherwise, all of this is exactly what we've done before. No different. Now let's look at another example. Now, of course, we can do shifts and things. We can look at this in terms of vertical upward shifts. We can do vertical compression. We can do all kinds of things. So let's try this one. The WebAssign will give you plenty of practice with this. And don't just look at this and use a fancy graphing machine or online grapher and get absolutely nothing out of this. That will be a complete waste of time. The idea is that Professor Ron uses the calculator where we need a nice calculus approximation, where we've done things, where we've done an exact calculation, and we need a nice decimal approximation that is due to the fact that Newton and Leibniz discovered the calculus that can do that. So again, focus on the art of doing mathematics. We cannot claim the math that we do if we don't do it. I mean, I know that sounds ridiculous, but it's the truth. Do not claim something you don't do yourself. If we are very grateful for our Google Calculator. If we've got clients, we need to give them an approximation so that they understand. They'll look at our exact answer and be befuddled. So we want to be able to help our clients. So that's when we're very happy to utilize that. But we give the credence and we give the output to the Google Calculator to say, okay, now we use Google and we get this nice approximation. Before the calculators, we would have to use tables, and that would take some extra time. So at least the Google Calculator has allowed us to do the computation approximation in a quick way. So now let's look at this particular graph. It's similar to the last one. We still don't have a shift yet. I want to preserve that for the last one so that we're ready for it. But notice here, this is very similar to the last one, but we have this upward V shift. So first, notice this part right here gives us amplitude and everything. So don't even worry about that. I'll just say graph 1 complete cycle. And the complete is overdone, just graph 1 cycle. So we want an interval of periodic length. So now we can say amplitude. We'll just go ahead and get used to writing this down. Amplitude will be the absolute value of 1/3, which is 1/3. That is A equals 1/3. And then the period, we've got K is equal to pi. So the period equals 2 pi divided by K, which is pi, and that leaves us 2. Well, there we go. We've got a period with no pi's in it. Well, that's easy enough. Big break. But of course, this is a compression, is it not? And that's easy to break that up into 4 pieces. And then of course, there's no shift. So I'll just write this. I didn't write that on the last one, but no shift, no horizontal shift. Let me be specific about that. We do have a vertical, so I'll just say no horizontal shift. So again, you can put extra steps here, less steps, your choice. As you get comfortable with this, you can practice whatever mechanism you like to get to the punchline. So now we can just say, okay, our parent function is cosine x. So first we'll do the H compression by pi. So this gives us cosine pi x. So this is exactly what we've done before. And of course, we have vertical compression here by 3 because we're going to make it smaller by a factor of 3. So V compression by 3. So this gives us 1/3 cosine pi x. So we've compressed horizontally and vertically, and then we do an upward V shift by 3, and that's easy. Upward V shift by 3. So this gives us 3 plus 1/3 cosine pi x. So no guesswork here. And so if you use Professor Ron's principal points, you're good to go. So let's do the principal points of the cosine. So we remember these vary because they're shifts. 0, 1, pi over 2, 0. Just use your unit circle. Pi, -1, 3 pi over 2. If you look at the practice test and the Smart Pen videos, you'll see these. And then 2 pi, 1. So we cycle back around. So 0, 1 here, 0, -1, 0, back to 1. So H compression by pi, so we divide all of the x coordinates by pi. So we get 0, 1, 1/2, 0. And then of course, I won't do the common denominators here. That'll be clear, but again, we did it with the last one because it wasn't as clear. Divide by pi, we get 1. Divide by pi, we get 3/2. Divide by pi, we get 2. So of course, at this point, if we do this first, these two should correspond. But if we do a shift or something before we do this, then they won't necessarily correspond. It'll just mean that the length of the interval should be that. So be careful how you test things. So now we do V compression by 3. So divide all of the y coordinates by 3. So 0, 1/3, 1/2, 0, and then 1, negative 1/3, and then 3/2, 0, and then 2, 1/3. So that gives us the vertical compression by the factor of 3. And then lastly, we want to do the upward shift vertically. So we're just going to add 3 to everything. Now notice, since we've got all these 1/3, 3 is just 9/3. So we can use that to make our algebra easier. So this will be 0, and that'll be what, 10/3. And then we have 1/2, that'll just be 9/3. And then we have 1, and so negative, so that's going to be 8/3. So 1, 8/3. Not a whole lot of space with the very, you know, smushed together, so to speak. 3/2, 9/3. And then back to 2, 10/3. 1 plus 9 is 10, giving us, excuse me, 10/3. So now you can see with this amplitude, these points, the vertical points aren't very spaced. We have that kind of median line, 9/3, which kind of acts as the new 0. And then above the 9/3, we go up 1/3 to 10/3, and then below the 9/3, we go down to 8/3. So that kind of really smashes things vertically. And then of course we have the compression horizontally, you know. So the idea is that, again, nothing new, just now we've relieved ourselves of the pies. So now we can get a picture of this, get one complete cycle. Now I'll spread this out a little bit since we have, you know, kind of an interesting situation. So once you do this, it's really easy to actually check out which graph is correct. So we'll go ahead and look at this. We'll spread this out 0. I want you to always spread things out so you can see it. Don't write it microscopically. So 1/2, and then a 1, then a 3/2, and then a 2. So that gives you a nice space horizontally. And then for here, we've got 8/3. So we'll just we'll spread this out a little bit. So we'll just say, let's see, how do I want to do this? I'll go in 3s. So we'll say 1, 2, 3, 4. So we've got 6/3, 9/3 right here, 10/3 here. So this, you know, I don't have a whole lot of room, in 8/3 here. So this graph is going to be right in that little band right there. So we have 0, 10/3. So this is going to be like the little median line right there. Then 1/2, 9/3. And then, of course, I could have just cheated and spread this out more, but I'll try to be realistic here. 1, 8/3. I didn't do a very good job of spreading that out. Let's see here. Let me do this. Let me move this over a little bit, get these a little bit better space. That's just not good. So about right here. So 1/2, 9/3. And then 1, 8/3. And then 3/2, 9/3. and then 2 back up to 10/3. So now I can go ahead and draw. It's nice and spread out. So we got a nice spread out curve. And so we can kind of, there we go, now a little bit. So what we're seeing here is that it gets really bunched. You know, if I spread this out a little bit, it would look more like the standard sine curve, the standard cosine curve. But notice everything's been compressed. There's more obvious compression vertically because I didn't spread out this scale as much. Here I spread out the scale quite a bit, but I guess maybe the way I set this scale here, these numbers are a little bit closer together. So you see more compression here, but it still has the basic shape of the cosine curve. When we look at this, it's been shifted up. The horizontal component has been compressed. So we go from a period of 2 pi down to 2, and then we go from an amplitude of 1 down to 1/3. So we can see more of the compression here in the y component, the way I've scaled this. So again, when you do this type of work here, that's the new curve. And so again, 0, if you wanted to, you can go in and just plot these. One, 8/3, 3/2, 9/3, and 2, 10/3. So again, the new graph is completely determined by these points, and then we just fill it in knowing the shape of the parent function. Again, a nice cosine curve, but again, compressed in both directions. Now, like I said before, depending on how the scales are chosen, that's going to have a direct impact on the way the graph is shaped. And since my scale here on the y-axis was smaller, you see the compression. But really everything is given by these points here. So we can see that the maximum value of the function is 10/3 and the minimum value of the function is 8/3. We have this nice bounded function. This allows us to actually figure out the upper and lower. And so this actually turns out to be a absolute maximum of 10/3 and an absolute minimum of 9/3, excuse me, of 8/3. So again, this process reveals many ideas about the function that again, as you work through this, do as many steps as you need, but do not guess. If you need specific points, move a couple of these. You don't have to move all of them, but if you move these particular 5 points, you've got the basic points of the curve. You have the max and the min, so to speak, and so you can easily draw it. Again, it's not Rembrandt, but it certainly gets the job done. Now, let's look at an example where we actually have a shift horizontally. So let's look at this one. Again, you can make these up. Now that you see how they work, you can make up your own problems with your own numbers. So we have y equals 1 plus cosine 2x plus pi over 4. Now, of course, you know, depending on what numbers you choose, the arithmetic can be good or bad, but the beauty of this is that no matter how horrible the numbers are, the approach is always the same. Notice here, this is not factored. We see that the k is 2, but we need to figure out what the shift is. So the first thing we're going to do, again, we want to graph a cycle of the periodic function. So when we look at this, we're thinking, okay, let's go ahead and factor. Let me write it in a more user-friendly way. So we can put in we have the 2x. So now what we can do is put in the 2 here and then the 2 downstairs. So just multiply and divide by 2. A lot of times when you factor, if you do this first, then the factorization is a little bit easier. So this will give us 1 plus cosine. And now we can factor the 2 to get the k. And that leaves us x plus pi over 8. So again, when you multiply through, you get your pi over 4 and your 2x as we had before. But notice this is a plus, so this will be a minus minus, which will give us a shift to the left. So again, the idea here, if you want to think about this, this is right back where we have f of x plus h. So this is going to be a left shift by pi over 8. Again, we're going to have a horizontal compression by a factor of 2, and then we're going to have an upward V shift by 1. So at least this gives us practice with the shift. So remember, because of the plus, this will be a shift to the left. So let's go ahead and write this down. So now, if you will, what's interesting about this particular function is that the amplitude is 1. Let's go ahead and write all this down. Amplitude is the absolute value of 1, which is 1. That is A equals 1. And now over here we see K is 2. So the period equals 2 pi over 2, which is pi. New period of pi. And then we have a horizontal shift, H shift. This will actually be negative pi over 8, which means left shift, because we have the minus minus. So the horizontal shift is actually negative. So this is a left shift by pi over 8, just like we did before. No difference. I mean, it's the same thing. I mean, the beauty of this is that we didn't have to learn much new mathematics to do it. We're just piggybacking on the old stuff, which is what you do in math anyway. You learn new stuff about things you already understand to move them to the next level. So now if you want, let's go ahead and do our transformation. So our parent function is cosine x. And if you will here, we can go ahead and do the H compression and then do the shift. So do H compression by 2. And now we can replace x with x plus pi over 8. So we do left shift by pi over 8. So this will give us cosine 2 x plus pi over 8. We can be a little bit more relaxed with the brackets and things. When we do this, we know what it is and we write neatly. And then, of course, we do the upward V shift by 1. Upward V shift by 1. So this will give us 1 plus cosine. Well, might as well go ahead and put those in. 2 times x plus pi over 8. So again, we're just, when you get to calculus, if you see functions like this, you'll think of them this way. Calculus won't be very helpful graphing something like this. You'll still use transformations because this is quicker, much quicker. The calculus is when you've got more exotic functions where you can't do this type of technique very successfully. So now let's move the principal points, 0, 1, pi over 2, 0, pi, negative 1, 3 pi over 2, 0, and then 2 pi, 1. So I don't say, well, logarithm is the power of the base. We don't have that with the sine and cosine, but you will see the sines and the cosines mixing with the logs and the exponential functions when you do product rules and things and integration by parts. So that'll come later. So now we'll just do the h compression by 2, which means divide all of the x coordinates by 2. So we get 0, 1, pi over 4, 0, pi over 2, negative 1, 3 pi over 4, 0, and then divide by 2, we just get pi. So again, divide by 2, we get a 4, divide by 2, divide by 2, here we get a 4. So we've got the new principal points on the x-axis, interval length pi. All of the coding is right in the intervals, in the ordered pairs. So now we do a left shift by 8, pi over 8. Now this is where I want to go ahead and do another transformation first. Let's go ahead and write everything in terms of 8. This is fine the way it is, 0, 1. This will just help with the arithmetic. So we'll do 8, 2 pi, and then we'll do an 8, and that'll be a 4 pi. And then we'll do an 8, that'll be a 6 pi. And then we'll do an 8, which gives us an 8 pi. So just write everything in terms of 8. That way you can do the transformation easier. And then you don't have to just do it on the fly. So now we want to subtract, in this case, pi over 8 from all of the x coordinates. So we get a negative pi over 8. And here we get a pi over 8 when we subtract 1. Here we get a 3 pi over 8. And now a 5 pi over 8. And then a 7 pi over 8. So it probably is better to go ahead and convert to the denominator here to save yourself the pain of having to do it, on the fly. This way we just, and again, always check your coordinates that you just were a court reporter in writing, because it's easy to make a typo. But here, again, when we divided by the 2, we convert to denominator of 8. So we see, we can check the spacing. Here we've got, the 2 pi over 8, 2 pi over 8, 2 pi over 8, 2 pi over 8 spacing is good. Then subtract 1 in all the cases. 4 goes to 3, 2 goes to 1, 6 goes to 5, 8 goes to 7. Simple. If you do things with the symbolic computation, which is what I've been teaching from day one, even though I know some of you don't like it, you can riddle your work with errors, or you can do it this way and get it correct. I think that the difference that's going to be in the success with STEM is your willingness to take on techniques that make you better, and this will make you better. And so now the last bit, all we have to do is add 1 to all the y coordinates, because we have an upward v shift by 1. Well, how simple is that? It's so easy, we make a mistake, right? So we have negative pi over 8. So we get 2, and then we have pi over 8, gives us a 1, and then 3 pi over 8, that'll give us a 0, and then 5 pi over 8, 1, and then 7 pi over 8, back up to 2. So adding 1, we get 2, 1, 0, 1, 2. So at least when we do the, let me go ahead and adjust the focus. When we do this technique, it's really easy to check the work. And so now this identifies the new graph right here. Here's our new graph. So now we can plot the points and fill in the curve, because that's what we do, right? Now notice this also helps you map out the x-axis. as long as the points are correct, it doesn't matter if the scales are a little bit obtuse, but we'll deal with it. I like to spread everything out on the x-axis because that's usually where the difficulty is. The y-axis is usually simpler. So, you know, and if you really want your curve to look good, you can just be arbitrary about how things work and not worry about it. So that'll work too. So let's go ahead and plot these. We'll just equally space them. So we'll have a negative pi over 8. Then we have the 0. Then again, equally spaced, pi over 8. And then we've got 3 pi, so we've got the 2, and then the 3, and then the 4, and then the 5. And then we have the 6, and then the 7. Again, you know, not perfect, but equally spaced. So these 5 points, 1, 2, 3, give you 4 intervals to plot the principal points. And then now we can get, I don't know, what do we got? 0 here, and then we have, let's spread this out a little bit, of 1 and a 2. That way we don't have the microscopic graph we had the last time. But it certainly, the smaller it is, the harder it is to draw. So here we have negative pi over 8, 2 right here. And then we have pi over 8, 1. And then we have 3 pi over 8, 0. And then we have 5 pi over 8, 1. And then we have 7 pi over 8, 2. Again, you know, you just eyeball it, and it's not going to be perfect, but that's okay. So now we want to draw the curve, filling in the points. So remember, when you think about the cosine curve in all this, we haven't reflected anything. So the shape will come down like this. So we're not inverting the shape. There you go. So now what we see, again, this is where you need to be mindful of things. When you start reflecting things give you an inversion look. But here, all we've done is we've done a compression horizontally, we've done a shift to the left, and then we did an upward V shift. So the shape, as far as the inversion, is the same. We just simply have to draw what is a cosine curve. But now what we see is that the curve is shifted. Again, with this 1 here, all of the values now are non-negative. We see the output, again, the output here, all non-negative. So we shifted this curve so that the minimum now is 0 and the maximum is 2. With a bounded function, you do have the luxury of really understanding the function very well. Sines and cosines, because they're bounded, do present some really nice characteristics that help us in computation. With that said, though, they can be extremely difficult to deal with. But this is what I'm talking about when it comes to symbolic computation here. You don't need any decimals. It's like doing the half-life problems. At the very end of the problem, or the radioactive decay or instantaneous growth and decay, whatever, Newton law of cooling, we have exact computation. So here, we don't have to worry about filling up our page with a bunch of approximations that are completely unnecessary. This completely identifies the curve. We scale the axes based on these points. And then, of course, you just keep continuing this way and continuing this way. This is a complete cycle. We're done. The curve looks just like this, and you replicate this over and over. And with these points, you can generate any new points. You can add the period to these points and get any point you like, in pi in this case, in pi, to get any point on the curve with the same output. So the beauty of the sine and cosine functions is that they have so many nice attributes that make their analysis very straightforward. And this is a key example of how we can use what we already know with some nice computational execution to produce a very seamless graph. Again, no approximations. And then, of course, if you want to go ahead and plot all of these, you can, like we did on the last one. Now, lots of times as you take your physics classes, you will have functions that there's a, for instance, that replicate the harmonic motion. And for instance, there's a Webber-Sein problem. It's really like a physics problem. It goes like this. We have the displacement. They use a V. I guess I should really write this as S, because yeah, let me just write this as S. I'm not going to use a V. They use V in Webber-Sein, but then that makes you think velocity. So I'm going to use S. I'm going to say S of t equals 7/10 sine of 920 pi times t. And this corresponds to displacement of time, of the time. This is basically a tuning fork. You know, tuning forks kind of look like this. You know, they have something like this. A tuning fork looks like that. And you touch the tuning fork to a surface, and then it vibrates at a particular frequency. And what this function is doing is basically representing the displacement of the time, and that's what we call the little branch there is called a time. So this is the displacement of the time. So that right there is the time in millimeters at time t seconds. So this tuning fork vibrates and the time just moves back and forth. You know, it's imperceptible to the human eye. And so again, since we think about the cosine and the sine curve as being sinusoidal in the sense that they are periodic, we think of harmonic motion. So you physics geeks, when you get into your physics, you're going to have a great time because you're going to get to use all this math. And so this time is just moving up and down in harmonic motion. And it's modeled by a sine function, which is an excellent example of a periodic function. And this is basically sines and cosines are the backbone of the Fourier analysis, which some of you will study when you get to the university, if not before. And so what we have here is a function that's similar to what we've been graphing, but the numbers look a little bit different. So here's what we're asked to do. So again, you've got this time that vibrates like this, and you're thinking, okay, well, let's write down the amplitude. The amplitude will be the absolute value of 7/10, which is 7/10. That is because A is 7/10. There's no horizontal shift here. And notice the independent variable is t for time in seconds. And so well, let me just write K equals 920 pi. So the period, remember, the smallest positive number for which the sine and cosine functions are periodic is 2 pi. So now we get 2 pi divided by 920 pi. Okay, the pi's absorbed, and that'll just give us 1, so we get a 4 and a 6 and a 0. So you're thinking, the period, wow, that's small. That's a small period. I mean, you know, okay, that's very small, ladies and gentlemen. So you're thinking, interesting. So we'll work more with this. So now there's one other thing that they describe in this function. When you take the reciprocal of the period, that is, we define frequency. This is, again, is a physics definition, as 1 over the period. Now remember, this is the independent scale here. So this is in seconds. Time is in seconds. This is the independent axis. And so 1 over the period will actually be cycles per second. So this will be 1 over 460, which is 460 cycles, cycle being a pure number per second. So that's what I mean by imperceptible. You can't see that. You know, that's a vibrational frequency of going through the cycle. Like here's one cycle up and then back. 460 of those in 1 second. You can't see that. So when if you've ever had a tuning fork and you strike it on a desk or something, you hear the resonant sound, and if you touch it to yourself, it'll stop, but you can feel the vibration as you dampen it. So this is amazing. So again, when you study your physics, you will definitely work with the sines and the cosines. And now, of course, you're thinking, well, what would this look like? Well, this is easy to graph, but we use the same ideas we did before. So again, to get the principal points here, we just want to take a quarter of this. So we'll say, so this implies 1 over 460 times 1/4. So that'll give us a 0, and then we've got a 4, and then a 2, so that's 18. So 1 over 1840. You're thinking, these are tiny numbers. And so now we can think of principal points. So what's going on here? We're doing, and this is where we can kind of cheat a little bit, but I'll go ahead and write it out like we did before. We have sine t as our principal parent, and then we do the H compression. That's some serious H compression by 920 pi. That's like seriously compressing something. So, ouch. So we get sine 920 pi t. And then we do vertical compression. So vertical compression by 7/10. So in this case, well, actually we actually reciprocate that. When the number's less than 1, but I guess, what did I do on the last one? Let me look and see what I did on the last one. How did I write it? Yeah, I did reciprocate it, and that's what I normally do. So by that factor, we're making it that much smaller. So this will be 7/10 sine 920 pi t. So in this case, when we think, like, if we have a vertical compression by a factor of 3, then we're multiplying or dividing the y-axis, y-coordinates by 3. If we have a compression by 10/7, we're dividing by 10/7 or multiplying by 7/10. So that's consistent with the way I've been teaching you. It just seems a little bit odd because these are interesting numbers. So now you're thinking, okay, well, we're good to go. We can get our principal points. So we have what, 0, 1. I don't want to shortcut this. I want to do all the details so you feel comfortable. Pi over 2, 0, 0, sine function. pi over 2, 1, pi, 0, 3 pi over 2, negative 1, and then 2 pi, 0. So now we do the vertical compression, and we can use these numbers here. So notice I'm going to go ahead and write them out. We're going to have 0. We're going to have 1 over 1840, 2 over 1840, do it symbolically, 3 over 1840, and then the last one, 4 over 1840, is just that number. So we do this symbolically. So we got 0, 0, and then we have 1 over 1840. Again, you divide by 920 pi, that gives you the 1 over 1840, comma 1. And then you divide this by pi. This will give you 2. You get the 960, but then we get the common denominator of 1840. So this way we have a nice computation via this calculation. And then 3 over 1840, negative 1, and then 4 over 1840. We get the common denominator and everything by symbolic computation with what we've done here. So we get this for 3. And then lastly, we multiply the y coordinates by 7/10 or divide by 10/7. So we get 0, 0, 1 over 1840, 7/10, 2 over 1840, 0, 3 over 1840, negative 7/10, and 4 over 1840, 0. So the idea here is I didn't just want to wave my hands over this and say, okay, well, clearly it's obvious what you do. No, it's exactly what we've done before. It's just now the numbers aren't user-friendly. But if you do this like I've taught you, you will have no problem getting these numbers. You apply all of the techniques I've taught you and then generate these because you've got the subinterval length and just 1, 0, 1, 2, 3, 4. And then boom, these numbers are generated for you already, which we could have done the other times. We could have done this also, but the numbers were easy and we dealt with it. So now when we draw the graph, let's go ahead. We've got enough room right here. So now we can go ahead and mark off 7/10. So let's just say we like here, we'll just spread it out because we're, you know, we have the luxury of simple points here. So you can do this in your physics class and help your physics professor who may not like math. Well, physics professors have to like math. There's nothing, wouldn't make any sense otherwise. So we have 1 over, let's see, go ahead and map this out. 2. Yeah, let me spread these a little less vigorously so I don't have to cheat at the end. Let me do this. So we'll do 1, 2, 3, 4, 5. So we've got 1 over 1840, 2 over 1840, 3 over 1840, and then let's see, 0, 1, 0, and 4. I didn't need that extra one, so because I got my 0 here, so I don't need that one. So I've got 1, 2, 3, 4, 5 points and my 4 subintervals. And so 0, 0, then 1 over 1840, 7/10, and then 2 over 1840. This is basically just generating the points, which is the hard part. The graph is easy. In your mind, you know what the graph looks like. 3 over 1840, negative 7/10. And so what you're saying is that you can just gloss over this, but see that this is just a basic sine curve that's been horizontally and vertically compressed. When you take university physics and you've had your calculus, then this will make more sense. Physics without the calculus is not the best, because you can't really understand the mathematics if you don't do the calculus. So when you look at this, and of course it works fine, it's just that you have more formulas and less derivations. But now what we can see is that when we want to describe, say in a physics lab, maybe this was part of a laboratory exercise, and you were working with a tuning fork, and then you had to map out the displacement. So again, you've got this as one cycle, and as we computed, there are 460 of these cycles in 1 second. So that, I mean, it's amazing. It's amazing vibrational. I mean, when you think about physics, ladies and gentlemen, physics is like as at Texas A&M and at Carolina, all the physics professors say that physics is the mother of all science. It begins and ends with physics. And then, of course, all the math people say, well, without mathematics, we don't have anything. So it's one of those things where I think the physicists put up with the mathematicians because they know they can't do their craft without the language of mathematics. And so now what you can see is this gives you a picture of what this tuning time, the tuning fork is doing, the time being this part that's vibrating at this particular period and this cycles per second. And then this just gives a nice model of what the displacement is doing. And then what you can do later is, as you get to your calculus, you can take the derivative of this and actually describe the velocity at which the time is moving, and then even acceleration. So the thing is here is that when you get through your calculus and you get to your first differential equations course, you will study a harmonic motion in detail. And if you take more physics, you'll do even more with that. So there are lots of very smart mathematicians who figured out the mathematical elegance of the trigonometric functions. And what we try to do in pre-cal is give you a nice geometric yet thorough algebraic introduction to them so that you can navigate your physics course, and also that you can navigate the math as you get to the calculus of the trig functions. And as you do more and more math, you will have more and more elaborate ways of describing the trig function. But like I say here, we want to use everything we already know about the trig functions to push everything forward. Now, after this, what we're going to do is we're going to talk about the graphs of the other 4 functions and how we can manipulate those. But understanding these functions gives us the understanding of the tangent, the cotangent, and the secant and the cosecant. So we'll cheat. We'll use what we know about these functions to get the graphs of the remaining 4. So if you want to go ahead and read ahead with the trig functions, I'll be more than happy to post some more stuff so you can do that, and you can look at the videos, SmartPen videos and things if you want to get ahead. But just remember, I've given you a little extra time on your homework, and also the window of time for the test number 2 will be just like the first one. Make sure to have that completed by 11 p.m. on Saturday. Again, this is my consideration to you as online students that I would give to any online student that I would teach. Pick a time that is best for you, low stress, low anxiety. That's the whole idea. And so remember, on Thursday, there is no class. Like I say, take that time to rest or to catch up on your homework or to do some preparation for the test. I appreciate your attendance today. I think you're seeing that the trigonometry is really kind of nifty and very exciting. And we've got quite a bit left to do, but once we do that, we'll hit the conic sections and the sequences and series and be done with pre-cal. So everybody have a good day and good luck with your studies.
Thank you.
Thanks, everyone.
Thanks.